Hi, I'm Tim, and this video is about anti-gravity matter and NGC1277. I'm going to use a lot of terminology and concepts in this video that are explained in the overview video series that's linked to the Anti-Gravity Matter website. NGC1277 has been in the news recently. It's been reported as having particularly low dark matter content. So we wonder, can we interpret NGC1277 using anti-gravity matter instead? This is NGC1277. It's situated in the Perseus galaxy cluster. It's an ellipse-shaped object with a peak of luminosity in the centre. And most stars in the galaxy are around 11 billion years old, and there's been little star formation since then. This is the paper that's made the news. The researchers here took some measurements, including measurements at large radius, and they found that the dark matter content of the galaxy was very low. That's particularly interesting because one of the predicted effects of anti-gravity matter is that the apparent dark matter content reduces at large radius. This is due to the dynamic AGM lacuna being cancelled out by an anti-halo. These are two of the diagrams from that paper. On the left we see a plot of the velocities of objects in the galaxy relative to the galaxy centre. So red on the left is moving away from us along a line of sight, and blue on the right is moving towards us along a line of sight relative to the centre of the galaxy. On the right is the dispersion velocity plotted against visual radius. Dispersion velocity is a measure of how much velocities vary at a particular location. Dispersion velocity is very high in the centre, but dispersion velocity drops off towards the edges. This is a classic spiral galaxy with a rotating disk and a central bulge. The stars in the central bulge are going mostly in and out, and the stars in the rotating disk are going mostly round and round. The result is that in the centre there's a lot of variation in velocity at a particular point, and round the outside there's much less variation, and in fact there's a very clear rotating disk pattern. Now we're going to analyse this making the assumption that stars are in a circular orbit, and we can't do that in the central region because stars there are not in a circular orbit, they're in the central bulge. So we have to discard the data that's in this central region. And we're going to make a series of assumptions to do our analysis. NGC1277 is a rotating disk viewed at an angle. We're only going to use data where the radius is greater than 5 times 10 to the 19 metres. The normal matter content of the galaxy is modelled as being all at the centre because it almost all is. And according to the AGM theory, rotation of the galaxy has caused an AGM vortex, which has caused a dynamic AGM lacuna. There is no gravitationally attractive dark matter. We're assuming that the AGM lacuna is spherically symmetrical, and then we're also assuming that G equals AN equals AA, and DAB is 2 times 10 to the minus 19 kilograms per cubic metre. So this is the velocity data, and I've taken this data from a couple of the diagrams in that paper. And you can see that on the left, objects are moving away from us. On the right, objects are moving towards us, and the central region is the area that we have to discard. And if we interpret that and try to calculate the anti-gravity matter density profile, we end up with this. Generally, it's the shape that you would expect from an anti-gravity matter vortex. The density drop is a significant part of our assumed value of DAB, but it's not greater than our assumed value of DAB, so the density doesn't go negative. Around the outside, the density actually goes above DAB. This is an anti-halo, as predicted. And this ties in with the fact that on the velocity plot, the velocities fall off quite quickly at large radius. So we're discarding the inner region. We would actually expect the anti-gravity matter density profile to look like this in the centre. So a continuation of the vortex shape into the centre, and then a shared anti-gravity matter boundary around the central core. If the vortex was shaped like that, that implies that the total normal matter mass of the galaxy would be round about 10 to the 10 solar masses. So this is quite encouraging because this plot does fit the predictions of the anti-gravity matter theory. But what about star formation? In the overview videos, I've described the mechanism whereby spiral galaxies produce new stars. Now we have to remember that this galaxy is within the Perseus galaxy cluster. And also, as I described in the overview videos, a galaxy cluster increases the temperature of the anti-gravity matter, and that increases the pressure of the anti-gravity matter. When pressure and temperature are very high, that stops the process of creating and cooling molecular clouds and stops the formation of new stars. There is gas and dust in between the stars in this galaxy, but it just stays spread out and mixed with the anti-gravity matter, and it stays hot. That doesn't mean that the Perseus cluster has existed for 11 billion years. It could be that the precursor galaxies were elliptical galaxies, which also don't form new stars, and they've only fallen into the Perseus cluster recently, and they've only formed this spiral galaxy recently. What about spiral arms? Well, the drag spiral mechanism is also affected by temperature and pressure. Pressure pushes the star's anti-gravity matter boundaries inwards and makes them effectively smaller objects. This means that they disturb the anti-gravity matter less as they pass through it and experience less drag, and it also means that the drag tail is closed off more quickly after the star has passed, and that means that one star gets less protection from the anti-gravity matter wind by following the star in front. That means that the effect of the drag spiral mechanism is reduced. It also might be that there are spirals in there, but the image resolution is too low. So our conclusion? NGC1277 doesn't contain gravitationally attractive dark matter because dark matter doesn't exist. Its anti-gravity matter density profile fits the predictions of the theory, and the lack of apparent dark matter at high radius is due to an anti-halo around a dynamic AGM lacuna.